Hi, I'm Jerry Brinkley. My partner is Joseph Carpenter, and we're over the Boyles Law project. A sealed syringe contains trapped air at an initial pressure of 96 kPa and an initial volume of 18 ml or milliliters. The plunger is slowly pushed until the air volume becomes 10 ml, 10.5 ml. Assuming temperature stays constant, what is the final pressure of the air? The relevance to this question that Boyle's laws have is Boyle's law describes how pressure increases when volume decreases if temperature stays constant. Our syringe scenario is a direct real-life application of this principle. The problem requires actual numerical solving, not guessing or conceptual answers. The setup connects to earlier project parts where volume and pressure changes were introduced because it uses realistic values and real equipment.
Hello, Joseph Carpenter here. And for the benefit of the problem we're doing, we learned how to apply Boyle's law mathematically to a real situation. We learned how to rearrange the equation to solve for unknown pressure and why pressure change in small everyday systems and syringes and pumps, and to how learn how to keep unit consistent with gas laws problem. Other problems this prepare you for is air pressure changes and breathing, like lungs expanding or shrinking, gas compression and bike pumps and air tools, pressure changes and scuba diving or underwater physics, and gas expansion and balloon or shell containers. Alternate problems that we decided to scratch were like a gas doubling in volume, and what would happen to the pressure. This was a bit, conceptual with no like actual numbers to work with, so it wasn't what we want. And then a gas undergoes three compression steps, and one expansion. Calculate all for pressure change. And the reason we didn't do this was it wasn't focused fully on the boys' wall, and we wanted something exactly like that. So that's why we chose our current problem.
Development of problem. We want a sample every day. We wanted a simple, everyday tool, a syringe. To set up a familiar, the setup is familiar. We selected realistic volumes and pressures based on typical physics labs syringes. Only Boyle's law is required, keeping the topic focused. Why is it not too simple? Uh, our problem is not simple because it requires plugins and values, rearranging Boyle's law and doing the math. Uses non-round numbers, so you must calculate carefully. You can't solve it by memorizing a rule. You must apply the formula correctly. Why is it not too difficult? Only one equation and one unknown, P2. Straightforward algebra, no graphing, no multi-step process. Uses units commonly seen in physics, kPa and ml. Difficulties we avoided temperature changes that would require the combined gas law. We don't really want to merge too many laws. We wanted to focus primarily on Boyle's law. Avoided multiple transformations, too long and confusing. Avoided realistic values that would cause extreme pressure or tiny decimals. Uniqueness of problems. Most books use balloons or generic containers with rounded numbers. Our problem uses real physical device that students or us actually see and use. The numbers chosen mimic real compression experiments. What we added: a realistic drop in volume that mirrors real syringes compressions. A more practical initial pressure, 96 kPa, instead of actually 100 or 101.3 kPa. How our problem is above common problems. Feels like a real measurement, not just a classroom exercise. Requires attention to detail and careful substitution. Better connection to medical, engineering, and lab applications. Visuals for problem. Pressure and volume shown a pure inverse pattern. As volume goes down, pressure goes up. Follows the mathematical formula uh, P equals 1 over V. P is pressure, V is the volume, of course. And I got a little graph right there showing it. So you can see on the left-hand side, volume ml. As that goes down, the pressure kPa is actually rising. So you see it starts at 18, then goes to 96, then 15, then 115, then 12, then 144. You can see how it just keeps rising.
So on that, our formula for problem is the classic P1V1 is equal to P2V2, and the variables of those are P1 is our initial pressure, and our V1 is also our initial pressure, so therefore P2 will be our final pressure, and V2 will be our final volume. The unit we're using is kPa for pressure, and then ml milliliter for our volume. Both of the units will remain constant, and so is our temperature, which is a Boyles law requirement anyways. So going over here, we'll show you our solution for this problem. So what we are given for the problem is our P1 is 96 kPa, our volume 1 is 18 milliliters, and then the only other one we got is volume 2, which is 10.5 milliliter. So thus we will be solving for P2. The step 1 to write the whole formula, P1V1 is equal to P2V2, but since we're solving for P2, for step 2, we're going to rearrange the formula, so then we'll get P2 is equal to P1V1 divided by P2. Our step 3 is to substitute the value, so we'll get 96 multiplied by 18, which would then get divided by 10.5. So then our first step is to multiply 96 by 18, and we'll get 1,728 divided by 10.5. And as you're doing that, we'll get an answer of 164.6 kPa. And that is the pressure T variable that we're going for here. To verify our problem we have here is it reasonable? Yes, because the Boyles law, volume is directly inversely proportionate to pressure, so our volume decreased, so our pressure increased. So we saw our pressure go from 96 up to 165, which matched the inverse relationship. Our ratio here will be 18 divided by 10.5, which is around 1.71. If we check all of our units, our kPa stays consistent through this, and so does our ml milliliter. This connects to Boyles' law, that is exactly how gases behave in real compressed systems, and it shows that inverse pressure-volume relationship clearly that we have going on here, and it enforces why Boyles' law is used in engineering and biology.